Mr. Matthew, go ahead.
Thank you very much, Ahmed, and welcome everybody. It's great to have you all join in and be able to be beamed in across the world. So most of you are joining in from Egypt or nearby, and we've got a few in Aberdeen, which is where I'm based at the moment. So it's great to be able to share it across all of the world. Just as Ahmed mentioned there, please put some, if you've got any questions as we go, feel free to put them into the chat box as we go. I won't see the chat box until the end, but I'm more than happy that if anyone's got any questions as I go as well throughout the presentation, turn on your microphone and just interrupt and ask questions, and we can ask them as we go then. So don't feel that you have to wait until the end, but I won't see the ones in the chat until the end when Ahmed and I go through them. So yeah, great. Thank you, and we'll get going. So the presentation this evening, as Ahmed introduced there, it's about maintenance optimization techniques, and it's about two main areas that I want to talk about tonight. What are the building blocks of maintenance? So what are the foundations that you need to get your maintenance plan in order? And then how do you actually build a plan once you understand your options that you have at the time? So they're the two main things I'm going to cover this evening. Reactive maintenance. This is the one that we all know the best. And have a think about your own plant or your own facility when I'm talking through these steps, and see how familiar this feels. You have a breakdown that occurs. Then everybody's rushing around to get that breakdown fixed. So you do what we call a band-aid fix. You just fix it up as fast as you can with whatever information, with whatever tools you can at the time to get it up and running, because operations is putting all this pressure on you to get it going. The team's then overworked because they're stressed. They're all constantly just doing these quick fixes rather than the proper fixes. Because the team's overworked, the morale drops, people are getting stressed, standards are dropping, people are not happy with what's going on in the workplace because all they're doing is running around what we like to call firefighting mode. All they're doing is putting out these fires everywhere when things are going wrong. The maintenance plans are then missed because all you're doing is fixing problems rather than working on the scheduled plan that you have in place at the time. Because you're missing more scheduled maintenance, the backlog grows, you don't get those plans done, and then the breakdowns get even more. So you end up in this vicious circle of what we call reactive maintenance, where all you're doing is running around firefighting problems all the time. So how do you think we can escape that cycle? What's the way that you can get out of this cycle? Because you haven't got enough people, you haven't got enough money, you haven't got enough time to do any of it. So what do you do about it? The way you have to work on it is to develop a suitable maintenance plan. And to be able to do a good maintenance plan, you have to understand what are the options that you have to choose from to make that maintenance work for you. So in my experience of working in some manufacturing and refinery type of industries, you get a maintenance manager. They get put into charge of the job, and they want to make impression first off. So where do they go first? They cut costs. The easiest place to cut cost is on maintenance. So they cut spending in your maintenance because everything's up and running pretty well. It doesn't really matter if we cut a bit of money here and there in maintenance. After 2 years, this maintenance manager's done such a good job because they've saved all this money. There's no extra breakdowns. You're not spending any more on repairs. New equipment's not being bought. Done such a good job. Off you go and get a promotion. Then the next person comes in place. They have to take over from the last manager who's just done such a great job. How do you compare to that? Things eventually will start to break down. That maintenance manager comes in and things are starting to break down. Costs are starting to spiral. People are getting stressed. We're in this reactive maintenance mode all of a sudden. That manager then has two options. They can ask to spend more money, which they're not going to get because the last manager saved all this money and look how good they did. They didn't need all the money. So how do you catch up if you don't have all of that money to spend? How do you justify spending the money without looking bad? If you think back to what the basics of maintenance are, there's kind of two main areas that I consider to be important to maintenance, and it's the technical actions and the administrative ones. So the technical ones are where you're doing the tools, going and working on the physical equipment, putting the plans in place, getting the training and things. Then you've got the administrative actions where you're actually keeping your paperwork in order, logging faults, looking after the hours of work, and all those sorts of things. So the technical actions and the administrative actions work together. And the main purpose of maintenance is to retain the item or restore it to a state in which it can perform its required function. So this is our whole aim, our whole point of doing maintenance. We bought the equipment, or we designed the equipment to perform a function. All maintenance is doing is bringing it back to that function that it was originally meant to perform. So what we're trying to do is keep it in good working order, but at the minimal cost. So we want to do it as cheap as possible, but as long as it meets that function. So that term there, required function, is really important to define what we want our equipment to do before we even consider doing maintenance on it. Can we defer the maintenance? Okay, so the last person spent 2 years deferring maintenance, cancelling maintenance. Is that such a bad idea? Absolutely not. It actually has a really good place in our maintenance scheduling, as long as we do it the right way. So this is about 5 years old now, this quote that I saw in the news. But if you think about offshore oil and gas or refining or nuclear or something that's a really high hazard sector, you can't be complacent because accidents happen, environmental, safety, money. And people always will put off doing the planned maintenance in place of operations, because operations is the main thing that drives production, because production makes money. Maintenance doesn't make money. So operations always get that first choice over it. But we can actually defer the maintenance as long as we follow a process. And that process is what we call a management system, where we have to assess the risk and look at what the consequences are, making sure we involve the relevant people. And some of the relevant people there that Robert mentioned are the technical and engineering authorities, but you've also got the operations team, the maintenance team, and all of the other manufacturers and areas there. So we can defer maintenance. That maintenance manager wasn't doing the bad thing. The parts that they were doing wrong was just cutting costs. So don't do it for the sake of cutting costs. The reason we really want to review our maintenance plans are by improving health and safety and environmental. Reduction in cost. If our plant's not making money, we're going to go out of business. So cost is our primary driver. We want to reduce maintenance costs, reduce production costs, have less inventory because that costs us more money, and have less spare parts. Increase stability. If we know when we plan to do the work, when we need the labor, when we need the spare parts, we can actually make our process more predictable, which makes it a lot less stressful. That's getting us out of that reactive cycle. Okay, so make it predictable, make it stable, less stress. And another way we want to do this is what we call improving employee ownership. If we can get the operators and the maintenance team feeling responsible for the equipment, like they own it, they're going to look after it better. So maintenance has evolved over the last 100 years or so. If you think back to before World War I, so early 1900s, so 1910, roughly there, think about the type of equipment that was in the industry. Really big, over-designed, heavy engineering, slow-moving, you've got your steam power, you've got your big greased up chains, very slow-moving, strong and robust. They didn't break that often. You didn't have to do much to them. So the maintenance technique then was reactive. Fix it when it's broken. Once it breaks, not too much of a rush, get in there, fix it up. Then when the war came along, everything changed. Pressures increased dramatically. No longer could we not worry about maintaining our equipment, because now if our equipment broke down, we're not going to make enough weapons, aeroplanes, all these things that you need for the war. So the pressure rose on the operations teams, and we had to make sure that our equipment wasn't going to fail unexpectedly. So rather than just waiting for it to break, what they wanted to do was remove it or overhaul it before it broke. So every year, every 6 months, every day, whatever it's going to be, do some overhaul maintenance or planned maintenance. Then it changed again about the 50s, 60s, 70s kind of era. With the improvements in quality management, the improvements in lean, improvements in all of these areas, people quickly realized that it was not cost effective or not the most effective method to wait and overhaul it for the sake of overhauling it. What we want to do now is have a look at what the condition is and then maintain it based on the condition. So when we detect that there's a failure coming or detect that there's a fault on its way, we then fix it based on condition. So we've kind of got those three main techniques there: reactive, planned, and predictive or condition-based. Towards the end of the century, things moved into what we call proactive maintenance, and it's still using condition-based maintenance, but we're going to focus a little bit more on risk. So what's the potential risk of failure, and also be proactive where we're looking at the root cause of the failure. So you can see we're getting a little bit more advanced over that sort of 80 to 100 year phase, from the reactive to the planned, fix it before it breaks, to the condition-based, fix it based on the condition, to let's be proactive and stop it by breaking in the first place. So if you put that into sort of what I sort of call a maintenance hierarchy, reactive is your primary one, the old-fashioned way, and it definitely has its place in a maintenance plan still. Then you've got the preventive planned maintenance, your predictive and condition-based maintenance. Then something which I'll talk about in a minute called total productive maintenance. Then a little bit more advanced where we're thinking about consequence of failure and risk, which is reliability-centered maintenance, and the proactive style where we've got a combination of reliability and risk-based maintenance. So this is kind of your evolution or your sort of advancement in your choices of maintenance. So what, as an engineer or as a maintenance team, we need to pick what's the best plan for our equipment. So very briefly, as the things I've just covered here, I've put some pictures of some cars in just to kind of get a feel for the era that these happened. Every time I speak to somebody and I say to them, what do you think a mechanical engineer does? They always say to me, they fix cars, don't they? I was teaching a high school, so 50-year high school a while back, and they started to do an apprenticeship in mechanical engineering. And I said, oh, this is really good. You know, we're doing an apprenticeship. You're only 16. This is great that you're getting into such a really good industry. And I said, oh, why did you pick mechanical engineering as a course to do, as a stream? I said, what do you think a mechanical engineer does? And I said, oh, we think they fix cars. I said, okay, well, some might do. I said, so what do you want to do as a job when you graduate? Oh, we want to work offshore. So what do you want to work offshore for? And I said, because we can earn lots of money. And I said, well, didn't you say that mechanical engineers fix cars? And they all looked at me like they thought I was crazy. It's like, yeah, I think we've got a bit of education here as to what a mechanical engineer does. So I talk about cars a lot in these type of topics because people can relate a little bit to cars. So reactive maintenance here, identify the fault, isolate the equipment and fix it. Okay, so the failures there are obvious. That's what we call an evident failure. Fix it back to the condition. Again, the key word here is the intended function. We only need to have it running back to the intended function. We don't need to improve it. We don't need to do anything else. Predictive maintenance, preventative maintenance. So this was after the war came along. We're looking at interval-based, so scheduling the work based on weekly, monthly, yearly, whatever it's going to be, usually calendar-based, but it can also be meter-based. So it can be visual checks, things like lubrication, filter changes, what we call restoration, so we restore it, or we could discard it and put a new one into place. If you think about how we plan our planned maintenance, our preventive maintenance, we have to think about how this curve behaves. So on the y-axis, we've got the probability of failure. So at the bottom, 0%, at the top, 100%. And then as time goes along the x-axis, we get to eventually, at some point at the end, towards the end of the life of this piece of equipment, it then starts to wear out. So we hit what we call the wear out zone. and the probability of failure starts to increase quite a lot because it's hitting that wear out zone. So all throughout its life, there's always some slight probability that it's going to fail. It's never going to be exactly 0. So we've got some small chance of failure, but as it goes along, we hit what we call this wear out zone. What we want to do as engineers and maintenance is we want to try to predict when this end of life time is. So somewhere between the start of the wear out zone, this dotted, what I call the dotted line, and the failure, 100% chance of failure, we want to try to do our preventive maintenance before we hit this wear out zone. If we do it too early, we're going to be doing too much maintenance. If we do it too much after the dotted line, we increase the chance of failure. So we're starting to be a bit risky. But there's a few problems with that. The first one is that we assume that all of our equipment that we do planned maintenance on follows this classical failure profile. The second one is that the failure statistics are actually available. How accurate is the information we've got on the life expectancy of our equipment? And then the third big assumption is that all equipment is average. We've got this average graph for our average pump. But what about you've got 2 pumps sitting next to each other? Do they behave exactly the same way? Will they fail after the exact same amount of life? Even if you operate them the same, even if you run the same time through each, will they both fail? Will that dotted line be the same for both? It's unlikely. So why are we scheduling that dotted line for both exactly the same? How do we even know where that dotted line should be? So it's pretty unlikely we're going to have all, well, it's extremely unlikely we're going to have all 3 of these, but it's usually very unlikely we even have one of them. So I want to have a bit of my first case study here, and it's from United Airlines. So back in the 1960s, United Airlines had a load of aeroplanes, and their aeroplanes weren't as reliable as they would have liked. There was too many failures, too many accidents. So what do you do when you have too many breakdowns, more breakdowns than you would like? What's the first thing you do? If things are breaking down too often, we do more maintenance on them. So that's exactly what UA did. They did more maintenance on their aeroplanes. They did more planned maintenance because we don't want reactive maintenance for an aeroplane because it'll fall out of the sky. So we do more planned maintenance in the 60s. What they actually found was that the more maintenance they did, it didn't affect the reliability. It didn't make them any better. And in fact, a lot of the time it actually made it worse. So they're sitting around scratching their heads thinking, we're doing more maintenance, more overhauls, more scheduled changes, more lubrications, more checks, but our planes are getting less reliable or they're staying the same. What are we going to do about it? So what they did is they got 2 people to come in and do a commission to do a report called Nolan and Heap. And Nolan and Heap analysed all of the failures, and they came up with these 6 failure profiles. So you can see the first one there, A, is what we call the classical failure profile, and it's the one I just showed you before. So again, the y-axis is our probability of failure, our x-axis is the time. So A, as time goes on, it stays relatively the same chance of failure until it hits this wear out zone at the end. B, high probability of failure when we first install it, and then it follows the similar style of our classical failure profile. C, the piece of equipment gets more likely to fail over time. D, it's pretty reliable when we first install it because we've just installed it, and it then gets an increased chance of failure as its life goes on. E, it's just completely random all the way throughout its life. So almost think of about a light bulb in this case. You don't know whether it's going to go when the first time you turn it on. You don't know whether it's going to go 1 year or 5 years into its life. So that's almost your, not quite E, but it's something similar to that. And then we've got F, where it's really unlikely or high probability of failure at the start of its life, and then pretty random throughout. So what I want you to do in the chat box, I want you to type in which one do you think is the most common failure profile that they came up with when they did their study. A, B, C, D, E, or F. So for the aeroplanes in the 1960s, which one was the most common failure profile that they found? So we've got a B. So B is the good old bathtub curve. Anyone else want to have a go? Come on, there's more than that. B, B, B. Anyone else want to? I won't read your names out, I promise. Right. That answer is pretty typical to what I get whenever I run this survey. What they actually found is something completely different. 2% followed the classical failure profile. So 2% of equipment failures that Nolan and Heat found followed the classical, what we call the wear out. 4%, which is what everyone always assumes is the typical for the failure, the good old bathtub curve is the saying, 4% only of failures followed that. 5% is what we call the fatigue. So as it gets more along its life, it higher chance of profile. So 11% in total is what we call age-related failure. Only 11%. And if you think, well, you're only talking about aeroplanes, I'll have a look at these other two industries. The US Navy was done on submarines, and the manufacturing is manufacturing plants. I'll talk about the Navy one in a minute because it's slightly different. But you can see there, even then, we're well below 30% for anything. I think the Navy one's all that 23%, that's the highest. 68% followed F. So 68% of failures followed what we call infant mortality failure profile. Okay, so 89% of failures in this study were found to be random in nature. We have no idea when they're going to fail. Okay, so it could be today, could be tomorrow, could be a long time. And you can see there that all of these have different profiles, but they've all got this flat random. And again, if you have a look at the other industries, submarines, similar, manufacturing, extremely similar. The reason for the Navy one being different is because it's a little bit more regulated. So they have a lot more accurate information in the Navy because it's a nuclear submarine, and they have a lot more accurate calculations and information that they can base their decisions on. So it's a slightly different proportion from the infant mortality. While it's still very high in infant mortality, they have a lot better conditions that they run their equipment to. And I'll go through the reasons for that in a minute. So that's why it's a little bit less infant mortality, but you can still see it's really high. Huge amount of failures happen when we very first start something up or install it. Okay. The main two important discoveries that they found: scheduled overhaul, so planned maintenance, has little effect on the reliability of an equipment unless it's got the dominant failure mode. So when I say dominant failure mode, think of a beam, and that beam really is pretty easy to predict when it's going to fail because the main dominant failure mode is going to be fatigue or overstressed. Okay, so we can predict the beam breaking pretty well. So that's got a dominant failure mode. So that kind of doesn't come into this study because we can predict that pretty well. But if you think about a complex system, so pumping system or turbines or something like that, scheduled overhaul has very little effect because only 11% in the aeroplane industries get to that wear out and age related. So there's a huge amount of items that there's no effective form of scheduled maintenance. Okay, there's no point doing planned maintenance when we don't know when it's going to fail. So in this study, 89% of equipment has no end of life. Okay, it doesn't ever get to the end of life because something else makes you change it before it's going to break, overhaul it, replace it, do something. It never even gets to the end of its life. So what we have to do is think about it a little bit differently. We've got to make sure that we improve the design, buying and storing, the installation, and our startup and shutdown procedures. Don't do maintenance for the sake of doing maintenance, because the more maintenance we do, the more chance we've got of restarting that infant mortality curve. And if we restart the infant mortality curve, that probability of failure jumps way up. have a think about the last time you tried to tinker with something. I'll give it a bit of a clean up. I'll pull it apart, grease it, do it, you know, shine it up, make it look all nice and running again, put it back together, and it didn't work, or something started to go wrong, or it squeaked, or okay. So you tinker with something, you play with it unnecessarily, you're introducing the chance of doing something wrong, making a mistake, having a problem. So don't do unneeded maintenance. The better way to do it is to monitor the condition to detect when you think it's going to fail, then take action. So monitor it, be able to assess it's good, we don't touch it, or it's starting to deteriorate, let's plan maintenance in. So predictive maintenance is one of the most effective maintenance techniques you can look at. Visual inspection, you know, just look at it, listen to it. Vibration monitoring, so rotating equipment, put vibration sensors, ultrasonic testing, so thickness testing, check the oils, thermography, so using a heat gun on electrical conditions, electrical connections, non-destructive testing, so MPI for welds and those sorts of things. So make sure you involve the operators, checking for process equipment condition. Just the basics makes a huge difference. Get the operators and maintenance team to keep an eye out on these things. Look, listen, feel and smell. But we want to be more advanced than just spending money on predictive maintenance. We want to be proactive. Okay? We want to fix something so that it doesn't fail in the first place. So this is what we call sort of your root cause based maintenance. If you have a failure, see what the failure cause was, fix the cause. Don't fix the band-aid, because that's your reactive maintenance. That's your reactive cycle. Okay, so there's a lot of maintenance tasks that don't achieve anything because we're not in those first three graphs. Just like they found with the aeroplanes, some actually are counterproductive. So they make it worse and also achieve nothing. So not only do they do nothing, but you could be making it worse. So make sure that you're doing it, you know, with the right decisions in mind. The next one on the graph table, the hierarchy you had there, was what we call TPM. And this is sort of where the Toyota production system started to come in, the Japanese systems. So it's sort of where lean manufacturing came in. Again, it's the proactive sort of style where we're eliminating the potential of a problem. So eliminate it before it occurs. And it's all centered around these 8 pillars, or what we call the 5 S's. So we've got sort, standardize, shine, all of these basic things to keep. And the whole idea is to highlight where we've got a defect. Highlight where we've got a problem, fix it before it fails. Zero waste, zero defects, zero breakdowns. And that's all about these 8 pillars, in which a lot of you should look familiar if you've done things like ISO 9001, which is quality management. If you've done the environmental management, all of these management systems and ISO, the Deming cycle, the Plan, Do, Check, Act, they're all interrelated there as we come through. So out of that Nolan and Heap study, they actually did a paper on what they found. And the name of the paper was Reliability Centered Maintenance. So that's where the term RCM came first into play. It's looking at what the reliability of our equipment is and focusing on the consequence of failure rather than focusing on fixing our equipment. And it's based on a system, based on a logical flow process diagram. Okay, so we still want to know what the function of our equipment is, but what we're going to do is focus on what we have to do to keep it running to that function and look at what the consequences of that failure is. And what it does is it asks you 7 very process logical questions. What's the function of the asset? Okay, what does it do? What way can the asset fail to do that function? How can it stop delivering that level of functionality that we need? What causes that failure? When the failure occurs, then what? Okay, so what are the consequences of the failure? Now that we know the consequences of the failure, do we need to do something about it? Can we just let it run to failure and then have a spare part sitting there? So when our light bulb blows, we don't maintain a light bulb. we've got a stash of light bulbs in the cupboard. Or if it's got a higher consequence, what can we do to prevent it or predict the failure? So the condition-based monitoring. If we don't have a suitable answer for number 6, what can we do that's proactive, or maybe we need to redesign it? So the good part about RCM is it goes through this whole logic diagram and starting to build in what we call risk-based inspection, risk-based maintenance. Collect your information, analyze the risk, which is consequence times the probability, rank the risk, so we can do what we call an FMEA, failure mode and effects analysis, or something to rank the risk. Build your plan using the methodology of RCM. Now evaluate and mitigate the risk and the consequence. If we're not happy that the consequence and the risk are low enough, go back and reassess it. So it's a constant cycle, continuous improvement cycle of managing risk. If you're not happy with the risk, go back using the reliability-centered maintenance methodology. So I've talked about the airline industry, what the failure profile curves of that look like. So you're probably thinking, like most people, I get this question is, well, that's all well and good for an aeroplane. You know, and the aeroplanes are just, you know, one thing in the world. How does this relate to my industry? I showed you how it works for the nuclear submarines. Slightly different SKU, but similar. Our manufacturing is extremely similar to the airline industries. So here's an example, a case study of using this process for a subsea oil and gas, because you're obviously all here for the Subsea Society, the Egyptian Subsea Society. So you want to care about what your industry is, right? I've done this process in quite a few different industries myself, using sort of a combination of the full RCM and also slightly reduced, less man-hour related tasks. And the outcomes are always really similar. Okay, so I've done it in packing plants, refineries, production lines, oil and gas, all these different areas. So think about those results in a minute when we talk about here's our oil and gas. What's the objective? You always have to start with the scope definition. What's the objective of what we're going to do? We want to optimize our maintenance strategy. That's what it's all about. If we optimize the strategy, we're going to have all of those benefits that I spoke about at the start. Lower costs, higher predictability, improved safety, less stress, better employee ownership, all those things. So that's the objective. We want a more realistic strategy and to stop doing tasks that don't help us, because we've just heard that most of the tasks in a maintenance plan are not useful or actually causing us more trouble than what they're helping. So we want to establish what we have, the continuous improvement strategy for maintenance assets. This is where we want to get to, this continuous improvement. So how do we do it? Where do we start? It's pretty similar to those 7 steps we talked about there. Get all of your equipment in place. What's all of your equipment you're going to analyze and study? What are all the failure modes of that asset? So what's the function? What's the failure mode? What are the existing tasks that we've got to address those failure modes? Then we've got to decide, is the failure mode evident? So can we see that it's failed? Or is it hidden? Because if it's hidden, we can't see it. We have to go and seek out the failure, because we don't want to press that start button and find that there's a failure that was hidden we didn't know about, for us to get a leak, you know, oil leak into the ocean or something. So understand hidden and evident tasks, and then decide on whether we want to use predictive, reactive, or planned maintenance. All of the time we need to keep those 6 graphs in our mind. Do we want to do planned maintenance? We only want to do planned maintenance if we've got a pretty good understanding of that classical failure profile. If we don't have a good idea of that classical failure profile graph, we're wasting our time with planned maintenance. So we want to maybe do condition-based monitoring, but that costs us money and that requires access, which isn't always easy under the water. Or do we do reactive maintenance, wait for it to fail? Again, not always good if it's subsea. So we've got to really have a good understanding of what our choices are. After this study was done on this subsea system, what did they find? They found that they were doing a huge amount of unnecessary overhauls. Okay, so what happens in maintenance? when you want to make sure things are going to be reliable. We want to be a bit more comfortable in the fact that something's not going to fail under the water or up in the sky. We do more maintenance, don't we? How many times have you ever seen someone go to a maintenance plan and go, we've had a fire, you know what, I'm going to take out some tasks. It's always the opposite way. What we'll do is we'll leave all those tasks in, but we're going to add extra tasks now. We're going to do it twice as often. We're going to do more. So maintenance plans always get added to, never taken away. So you end up with a huge amount of tasks, specifically planned maintenance tasks, because that gives us that comfort factor. So they were doing too many unnecessary overhauls. In some cases, or a lot of cases, they were doing both overhaul and condition-based because it felt better to do that. Well, let's monitor the condition and we'll overhaul it as well, because then we can be double sure it's going to be good. Okay, so hopefully you get a bit of an idea now that that's actually not a good idea. A lot of the tasks were ignored because there was so many redundant or useless tasks that they just don't do them. Okay, or the backlog just grows and grows so they don't get done. How many of you can think about that in your plant? You know, how many tasks are there, they don't get done, or they get done, or they just tick off the box. You find that a lot is they'll just walk around to the check sheet and they'll just tick it off because they know it was done yesterday and they know it's a waste of time doing it today and probably tomorrow. So they don't get done. After the study, they actually took around about 50% of the tasks out of the maintenance plan. That's a huge number of tasks that they're doing for no reason, 50%. They decreased what we call intrusive maintenance, so where we have to pull it apart to check condition, or planned overhauls, and they increased the condition-based, so the non-intrusive work. What it did is it also gave them a more realistic view of the man-hours that were performed. Engineers love graphs, they love data, so here's a graph for you. What did they find? This is just for the subsea engineers tasks. They removed 35% of tasks that were duplicated, done more than once by the subsea engineer or by other departments that the subsea engineer was already doing. Plus, they took another 13% of tasks away, which were just not adding any value whatsoever. Okay, so this is a little bit more like the submarine-ish one where you've got pretty good information because the risks and consequences are so high. So you find that there's quite often not as many non-value adding tasks because they're a little bit more advanced with their predictions, but there's still a huge amount. So 40% of tasks were removed. 34%, the detail was modified, and 5% they extended the intervals. Only 13% new tasks were introduced. Okay, so I did this in a refinery. Just trying to think about which example I was talking about. I did this in a refinery, and I reduced the amount of hours that overhauls took, and I extended the intervals that the overhauls were done. By just using an Excel spreadsheet, getting the right people in the room, which is operations, maintenance, manufacturers, engineers, regulations, bodies and that, we saved 250,000 Australian dollars a year by having a team in a room for a week using Excel spreadsheets, using this philosophy. Now I have to say it took me a lot more than a week before that to plan it all, and a lot more than the week afterwards to put it all together again. But the team itself spent a week in a room going over all the information, plus my time, $250,000 of savings just from that one study, looking at what that is. In this instance, the man hours was actually increased by 14%, but what you're doing is you're reducing the cost, the likelihood of failure, because you're doing the tasks that actually add value. So that was just for the subsea engineer. For that one case study for the subsea system in total, 49% deleted, 13% new tasks, 5% extended intervals, 33% modified. Okay, think about how many tasks you're doing on your maintenance list. What if you removed 50% of those tasks off your maintenance plan? Just think about how much time and money you're going to free up. That's your first benefit. The second benefit is what happens if it doesn't fail anymore? we've increased or decreased the likelihood of failure because we're doing tasks that actually add value. Remove all the planned maintenance tasks that do nothing or cause us more problems. Do the tasks that actually make our decisions better, and we save more money. Now you can sleep better at night, right? So my 4 key takeaway tips. Start with leadership as deciding on the decision of the business, okay? The leaders have to be the driving, but it's the operators who are the front line of this. The operators operating and maintaining the equipment are the ones that are there seeing how it operates every day. They're providing that basic care, and by default, they're monitoring condition. Okay, think about when you get in your car to start in the morning. You can hear when it doesn't quite sound right, or it's driving a little bit funny, or it's pulling to one side. Take to the mechanic, they don't have a clue what you're talking about because to them it just sounds normal. The operators are the ones who can detect so many of these issues really easily because they're there. The maintenance and engineering team are there to support operations. Operations drive everything because operations make the money. Okay, so as maintenance and engineers, we are there to support the operations, but it's our job to make sure that the decisions that are made are based on the right information. And that right information has to be based on reliability-centered maintenance, total productive maintenance, risk-based inspection types of methods. They will help you choose whether you go for reactive, planned, or predictive options. And then don't forget the technology that's now available. 20 years ago, when we were doing these studies in a packing plant, I would have to go and stick a disc on the side of a motor, get a vibration probe, stick it on the side of the motor once a month, have a little pack of computer next to me where it uploaded in, go back to my office, upload it to my computer, make a graph out of it, look at the graph from last month, compare it to this graph from this month. It took so much time. Now we can have, with the Internet of Things, we can stick a remote sensor out into the an oil rig, send our information back, and artificial intelligence or digital twin can help us predict when that failure is. So our predictive maintenance is so much more accessible and so much better. So now what? Our maintenance manager is a happy person because by doing the proper plans, reduced costs, okay? So no longer does that last maintenance manager upstage us. We've actually reduced costs by doing it better way rather than cost cutting. The process is more stable because we're going to be able to predict when we're going to do the maintenance. And what's the business main aim? It's profits. Profits are up. Our maintenance manager, now you're on the path to promotion. So how can you become this person? Okay. How can you use these maintenance techniques to the best of your knowledge to save money, improve safety, be more predictable, reduce stress, and ultimately have a happier life? Because that's what we want to do, isn't it? We've got to make money as a business, but as a person, we want to have a happier life. So what I've done is I've put together a program just for the Egyptian Society of Subsea Engineers and friends, because we're all friends now. So anybody who's joined in or anybody you know there, I'm happy to put this offer to all of you and any of your contacts. 5 weekly group sessions of 3 hours online. So all of my training these days is online. I do training most weeks on things like maintenance and hydraulics and 3D printing and project management, those sorts of things, and it can all be done online really effectively. And in some cases, it's actually better. So I've put together a 3-hour sessions over 5 weeks where we're going to cover the traditional approaches, so reactive, planned, predictive. Then it's all about analyzing the failure and the criticality and risk ranking criticality using what we call FMEA. Understand how you can then use the RCM process to prioritize your tasks and pick the right tasks. And then you're going to do a practice where you actually get to put all this into action. So by the end of it, you'll come away with the tools, the templates, and the knowledge of how to do exactly the same example I've given you for Subsea. And I said I've done it in manufacturing with the same number of improvements, done it in refineries and oil and gas. So I've planned a course for just after Christmas, New Year's resolution, start of February there. And because I said we're all friends now, the normal price is $1,250, but I'm going to do it for a discount for you if you sign up to that. And if you want to do it in-house within your own business, I can give you an even better discount as well. So if you have a group session there. So if you're interested in that, as I said, I've set up a specific course just for us on Eventbrite there, Maintenance Mastery, ESSE. If you want to write that website there down, or go to my company website. So I'm the Director for Project Engineering Management Limited. I'm also the chair for the Institution of Mechanical Engineers, Scotland. So I talk to a lot of manufacturing and engineering businesses and business people and engineers and technicians and things. So, you know, I hear these stories all the time, this reactive maintenance story, this stress story, this whole, I don't know where to go. So hopefully that gives you a bit of an overview, a bit of better understanding of sort of when maintenance was, where it can be. And I'm happy to take any questions. I'm going to stop sharing and I'll jump to the chat box. But please feel free to stick on your microphone and ask me any questions you like. So if I just run through the questions there, yes, if it's mechanical, not just electric, if that's the graphs you're talking about.
Matthew, if you can just say the question and also say the answer for the sake of the recording, it would be much better.
Oh yeah, sure. So
yeah.
The first question was, I assume that all mechanical and not electronic equipment. So no, it's mechanical as well as electrical equipment. If you think about the tasks that people do for electrical maintenance, most of the time they do far less maintenance on electrical because they don't understand what the best task is. So how do you maintain a switch box, switch gear? To isolate it, you get a screwdriver, you check that all connections are tight. Because if the connections aren't tight, you could get a spark or a short circuit or overheat fire. So instead of doing that, why don't you leave it, open the door, get infrared camera and scan it with the infrared camera, and then it will tell you where all your hotspots are. Safer way because I'm not sticking a screwdriver in a box. Faster because I'm not having to check every connection, and I'm less likely to introduce a failure by over tightening things. So this stands just as much for electrical equipment as it does mechanical, but people understand mechanical better. So there is usually more duplicated tasks in mechanical, but under-maintained in electrical. What else have we got? I managed planned maintenance, preventive for Subsea 2 years. Okay, good. Hopefully you weren't that maintenance manager that cut all those costs. Yes, the recording will be made available for those of you who have joined in. I think Ahmed will give you access to the recording at the end of this. So if anyone's got a question, feel free to stick your microphone on as well. I'm happy to talk to you about any questions you've got or chat about them.
Yes, I have a question, Matthew, to ask, maybe to encourage others to jump in with their questions.
Yeah,
yeah, okay. For the analogy you use is if the equipment is working or is it failed. But there's an in between. Let's say if the performance itself is deteriorating.
Yep.
So how do you account for that in terms of your analogy?
Okay, so we've got 2 points on that curve. So if we think about our equipment's operating as normal, and then all of a sudden it has a failure, start of a failure. As soon as we can detect that start of the failure, that's what we call the potential failure point. So there's a potential failure started, but our equipment's still functioning, okay? Because what we've done at the start is we've defined what our equipment has to do to be able to function. So it's something with the bearing and it's rotating. So my bearing, let's say my shaft on a bearing is rotating, but my bearing's all of a sudden got a bit of a crack in it. One of the balls or the race has got a crack. So the potential failure has started, but my shaft is still spinning, so it's still functioning sufficiently. As the bearing gets more and more worn, failure, cracked, or whatever happens, it's still functioning, but you can see it's starting to wobble a bit, or it may be getting hot or something. So what we have to do is decide where that functional point is. Where it's no longer functioning suitably, that's what we call the functional failure. So maybe the vibration's so much on our shaft that we can't deal with anymore. It will then start to vibrate even more and then explode, for instance. So what we want to do is we want to be able to pick the point between the P, the potential failure, and the F, the functional failure, and make sure we do our detection in that point. If we do it before the P, we're not going to pick it up because the potential to failure hasn't started. If we do it after our F, it's too late because it's now failed. So we want to try to use some technique that gives us as big a window for P and F as possible. If I want to use sight only, it's only going to be when the shaft starts flapping around where I'll see it. Whereas if I'm using vibrational analysis, I'm going to detect it far earlier. So the trick is to use the right predictive maintenance without over maintaining. Does that make sense?
Yes, it does. Thank you very much. I would like to encourage others also to join in with their questions.
What happens if there is a situation when the method of maintaining improves? Are you talking about because of technology? So if we have a better way to maintain it, we have to review our maintenance plan. We got to go back to our management system and review the tasks that manage the failure of that equipment. So what we do is, rather than saying, well, we're going to use visual methods, we can now use transducers or something. So we have to continuously improve. So we just have to go back and renew it once we find that there's some better way of doing it. Okay, any other questions? Happy to stay on for a bit longer if you need. As I said, if you've find any questions later on, please feel free to go to my website there, projectengineeringmanagement.co.uk. There's an email contact me now button there. Send some questions through if you want. I'm happy to help with any areas that you need assistance with or something like that. I've got another question. You're welcome. Thank you very much. Okay, Ahmed, is there anything else that you've seen come through that I've missed?
I think the presentation is perfect as usual. I had the opportunity to hear it live from you before.
Yes, it's a different face-to-face version, isn't it?
Yeah, exactly. So I think there's no more questions from our participants at the moment.
Yep.
Last call. Do you guys have any questions?
Yep. As I said, just make sure that the two things you think about is the task that you're doing, is it appropriate for the consequence that you're managing? If you're happy for it to fail because you can manage the consequences, let it fail. If the consequences are too great, then you have to do some maintenance and think about, is planned maintenance going to give you the most accurate task to prevent that failure or predict that failure? Okay, well, thank you very much. Oh, hello. Just
sorry.
made it. Yes.
Yeah, I was thinking
No
about a question. So I'm from India, and then during this lockdown period, apparently there's been about 32 accidents in factories.
Yes.
And one of the things that I was thinking from a maintenance point of view is that when such an incident happens, that there are not enough staff, and whatever you would have generally planned to do as a maintenance activity, that's not happened, and
yep.
Such accidents happen. So what do you think would be the strategy for such periods when we don't have the dedicated staff on site to be looking at things and monitoring it on a daily basis?
Yeah, that's a good question. Because particularly in the last 6 months, as you said, because people are not on site as much, planned maintenance or scheduled maintenance there isn't being done, or we're not monitoring it enough. So what we have to do is think about the risk. It's all about managing the risk. What is the risk of it failing? If it fails, what's the consequence of it failing? So we can defer it, we can not do maintenance, we can do a whole lot of different options, but it all comes down to prioritizing risk. Some things, if the risk is too high, you have to have somebody that's going to maintain it. There's your justification as the engineer or as the manager or whoever is the one pushing for this to happen. The risk is too great to not maintain it, to not monitor it, to not do something about it. You put that to your boss and say, are you happy to live with this risk? They won't, because they're not going to want to put their name to having that risk, knowing that if it fails, it's them that goes to jail. So it's all about identifying risk. You can defer it as long as you've actually analysed what that risk is. Consequence and probability of failure.
Thank you.
No problem. This is one. I was speaking to someone last week who manages offshore assets, and this is how they're doing it. They're deferring a lot. Depends on what country you're based in as to what the rules are. But you know, here you've got the health and safety executive. They were saying something about you get one deference that they're happy to accept as long as you manage the risk of what that is suitably. Document the risk. Every decision you make has to be documented. Cover yourselves with the reasoning for it. Okay, if you get, you know, things are still going to always fail. You know, no matter what graph you look at, there's always some probability of failure. You can't remove it altogether, but you have to manage that what if scenario. Okay, last chance. So thank you very much for having me join in tonight. It was really good to be able to be here and talk to so many people from so many different locations. So if you've got more questions, feel free to harass me, bombard me. I'm on LinkedIn, I'm on Facebook and all those things. So chat away.
Thank you very much, Matthew, for your time. It was not only this hour. We took some time to arrange for this meeting. Thank you for your time and for this presentation. Also, thank you everyone who jumped in tonight for 1 hour of maintenance.
Yeah.
We would like to welcome you to join ESSE all the time. We have a series of webinars coming along. Also, if you have any topics you would like to hear about or even to present, you can email us at egyptsseng@outlook.com. The email address is on the chat box.
Yep.
Recording will be available, so you can share this presentation with your colleagues if you find it helpful to them. Once again, thank you everyone, and we would like to see you again maybe in 10 days for our next session, inshallah, hopefully. Thank you, Matthew, once again. Thank you, everyone.
Thanks, Ahmed. Thanks, everyone.
Thank you. Thank you.